A ball is thrown vertically upwards with an initial velocity of 20 meters per second. So here's the situation. This here is ground level. I'm assuming that the ball is thrown from ground level. So at t equals 0, the first ball, that's denoted by the subscript 1, has a speed of 20. u1 is 20, because there's a second ball in this problem. So s equals 0 is the height above the ground of the ball initially. So the ball is just on the ground. Upwards direction is positive, or vectors pointing upwards. 1 second later, another ball is thrown vertically upwards from the same point with an initial velocity of u meters per second. So here's the situation 1 second later. Of course, the second ball is launched from the same point as the first ball, but I'm showing this on a separate diagram just for clarity. So this is the situation at t equals 1. So here's the second ball being launched at that instant. Its initial speed, u2, is given by u. Now the first ball is up here. So initially it was here, now it's here. Its new velocity, v1, is obviously less than u1 because this first ball is decelerating because it's acted on by the force of gravity. Its weight is acting on it, which means it's got an acceleration due to gravity of 9.8. The magnitude of the acceleration is 9.8, but the actual acceleration, a, is minus 9.8. See, the acceleration vector is pointing downwards, whereas we're taking upwards as being positive. So v1 is positive, u2 is positive, but g will be negative. So a will be negative. G is just the magnitude of the acceleration. A is minus 9.8. The balls collide after a further 2 seconds. So 2 seconds after t equals 1, that means t equals 3, the balls collide. That means that S1 will equal S2 for the balls. They're both at the same height above the ground, roughly. So we want to show that u equals 17.75. The initial speed of the second ball is 17.75. So the formula we use is s equals ut plus a half at squared. So we'll be using the fact that s1 equals s2. So what is s1? S1 is the height of the first ball above the ground. It's u1, which is 20, times t, say the height s1 at any time, plus a half times a is minus 9.8, so we get minus 4.9 here, t squared. So this formula gives us the height above the ground of the first ball. Now what about the second ball? Well, the initial speed of the second ball is u, which we don't know. Now what about the time for the second ball? We can't put t here. We can't write this down. I'll just show you. We can't write down ut minus 4.9 t squared. The acceleration will be the same for any object near the Earth's surface. Why can't we write this down? Well, you can see one problem with this. We want S2 at time 1 to equal 0, because the timer starts at 1 for the second ball. T equals 1 is when the second ball is launched. But if we plug 1 in here, 1 for t, and we're not going to get 0. We need to get 0. So we need to change the form of S2. What we do is we replace t with t minus 1. So this is a very important idea. If we have an object that's lagging behind another object, so this second ball is lagging behind the first ball by 1 second. So the timer starts at 1. So we replace t with t minus 1. Why does this make sense? Well, what do we want? We want the height of the second ball at t equals 1 to be 0, because it's just launched at t equals 1. And by putting t minus 1 in for t, that we ensure that that is the case. Because if we replace t with 1 here, we get u times 1 minus 1, minus 4.9 times 1 minus 1 squared. Well, 1 minus 1 is 0, and this is 0. So this ensures that we get 0. So that's one way to understand why we replace t with t minus 1. If the second ball was launched 3 seconds later, we'd be replacing t with t minus 3, and then this formula would describe the height of the ball above the ground for all subsequent times. Now we're given that the height of the first ball above the ground at t equals 3 equals the height of the second ball above the ground at t equals 3. They collide when t equals 3. So it's only a matter of just equating S1 with S2 when t equals 3. So S1 at t equals 3 is 20 times 3 minus 4.9 times 3 squared, and S2 at t equals 3 is u times 3 minus 1, which is 2, minus 4.9 times 3 minus 1, which is 2. So we just have to solve this for u. So I'll just write down the answer. That's straightforward. That's just basic algebra. U equals 17.75 meters per second. In part 2, we want to find the distance travelled by each ball before the collision, giving your answers correct to the nearest meter. Okay, let's see what's going on here. You might think that S1 is the answer. Let's just calculate S1, which is the height of the first ball above the ground when t equals 3. We'll calculate S1 at t equals 3. Of course, that's going to be the same as S2 at t equals 3. So we can use either of these, either S1 or S2. I'm going to use S1. We get the same answer, 20 times 3 minus 4.9 times 3 squared. We already kind of had that when we were calculating u. For that answer, we get 15.9 meters. Now, is that the correct answer? Is that the distance travelled by each ball? Well, it's possible that the first ball reached the maximum height and started to fall down again before the second ball collided with it. In that case, the first ball has travelled a greater distance than 15.9. Sorry, it should be 15.9. So the first ball could have went up, reached its maximum height, and started to fall down before the second ball collided. The second ball would have covered a distance of 15.9. That looks like the distance covered by the second ball. How do I know that? Well, if we look at the speed of the first ball, it's 20. But that's actually greater than the initial speed of the second ball, which is 17.75. So that tells us that the first ball went up, reached the maximum height, and started to fall before the second ball collided with it. The second ball could not have collided with the first ball before the first ball reached its maximum height, simply because the initial speed of the second ball, 17.75, is less than the initial speed of the first ball. So the second ball could never collide with the first ball when the first ball was on the way up. So the first ball was actually falling before the second ball collided with it. So 15.9 is the distance travelled by the second ball, and that can be rounded to 16 meters. We want an answer to the nearest meter. So that's for the second ball, distance travelled by the second ball. So how do we get the distance travelled by the second ball? Well, we notice that, by the first ball, we notice that when the first ball reaches its maximum height, its velocity is 0. So v for its velocity when it reaches its maximum height, and 1 refers to the first ball. So we've covered this kind of thing before. We just set v1 equal to 0. So v1 equals u1 plus a times t. Well, we don't use this formula actually because we don't know what t is. So we have to use the other formula, which is v1 squared equals u1 squared plus 2as. So v squared equals u squared plus 2as. And we set v1 equal to 0. So we get 0 squared, which is 0. And we can rearrange this to get s. S equals minus u1 squared divided by 2a. So that's going to be minus 20 squared divided by 2 times the acceleration. The acceleration is minus 9.8. Acceleration is negative because it's pointing downwards. We're taking upwards to be positive. So when we solve this equation for s, we get 20.4 meters. Notice that s comes out to be positive as expected. Upwards is positive. So the minus over the minus ensures that we get a positive answer. So when the speed is 0, that's when the ball stops. It stops instantaneously when it reaches its highest value. The distance is 20.4. So the total distance from here to here is 20.4, and we just subtract 15.9 to get this distance here, which is 4.5. So if we want the total distance travelled by the first ball goes up to this distance of 20.4, and then it drops down a distance of 4.5. So we have to take 20.4, which is the total distance, and add on 4.5. So to the nearest meter we get 25 meters. So these are our answers: 16 meters for the second ball, 25 meters for the first ball.